Welcome to Lecture 31, Your Place on Earth. This is the first lecture in the final module, Module 6, entitled Potpourri, and it is a real potpourri of different ideas, technologies, physics concepts, and physics applications. Some of the lectures in this module are outgrowths of some of the earlier modules. They're perhaps more complex material that wouldn't fit into those other modules. Most of them draw on ideas from several of the earlier modules and put together concepts that we wouldn't be able to deal with the subject matter of one of those modules alone. Module 6 is bracketed by two lectures whose titles sound similar. They both begin with Your Place. And so you might think, well, they're kind of similar. One is the first lecture, this one, Lecture 31, is Your Place on Earth. The final lecture is Your Place in the Universe. So they sound kind of similar. Nothing could be more different. This lecture, Lecture 31, is about a specific technology. It's probably the most specifically technological and, in a sense, the most contemporary technology I'll be dealing with in the entire course. This is a very specific lecture about a very specific technology that allows us to determine our place on Earth. Lecture 36, the final lecture, Your Place in the Universe, is a much more grandiose philosophical look at where we human beings fit into the universe, in particular, how the material of which we're made is descended ultimately from the stars and from the processes that began and shaped our universe. In between, we have more of that hodgepodge-like potpourri. Lecture 32, Dance and Spin, deals with rotational motion, something that might have fit into the second module but didn't fit, and that also has some specific implications ranging as far and wide as how the North Star will not always be the North Star to how medical resonance imaging works, or the fundamental principle behind it. Lecture 33, The Light Fantastic, talks about lasers. I said at one point the transistor may have been the most important invention of the 20th century, but the laser ranks right up there also. And Lecture 33 deals with the laser, how they work. We'll see a number of demonstrations of lasers in action. Lecture 34 is Nuclear Matters, a little bit about the atomic nucleus, its role in producing energy, its role in a lot of other important technologies, some of the dangers it poses, and so on. Lecture 35 is Physics in Your Body. We'll start out with a little bit about the mechanics of how your body works, but most of that lecture will be dedicated to medical techniques that use physics, particularly medical imaging, PET scans, CAT scans, MRI scans, bone scans, and that sort of thing. So it is a real potpourri of different lectures. We'll be shifting gears fairly rapidly from one to the other. Lecture 31, this one, Your Place on Earth, is about the global positioning system. The global positioning system is quite a new technology. It's been available to civilians in its full form only since the year 2000, and it only got into full implementation in about the year 1994, so it's a quite new technology, and it is already revolutionizing many, many areas of business, of commerce, of technology, of science, and so on. So we're going to look in this lecture at the global positioning system. In a sense, the global positioning system is an outgrowth of Module 2, again, when we had a lecture on Into Space, because the GPS system is based on satellites, and satellites are spacecraft, and they obey all those orbital parameters that we talked about in that module. But there are many other technologies involved in the global positioning system. So let me begin with a brief history of the global positioning system. And it's a brief history because, as I indicated, this is a fairly new technology. The first trial satellites for GPS went up in 1974 and 1977. GPS was initially conceived as a military project, and until the year 2000, it was in some sense exclusively a military project, in the sense that civilians were not allowed access to the most precise measurements it could provide. In 1978 to 85, the so-called Block 1 satellites were launched. These were the first generation of GPS satellites. The satellites are being continually improved. From 1989 to 94, the Block 2 satellites, some of which are still up there in more recent versions of them, were launched. And in 1994, the system became fully operational, meaning the 24th satellite was launched. GPS requires that there be at least 24 satellites up there at all times. In 2000, so-called selective availability, which is what made the civilian use of GPS limited in its accuracy, was abolished, and so the full GPS accuracy became available for the first time to civilians. So what is this global positioning system? Well, it's primarily, not exclusively, but primarily a space-based system of this so-called constellation of 24 satellites. So this is a symbolic picture of what it might look like. I haven't shown all 24 satellites, but there is this swarm called a constellation of satellites. There have to be at least 24 at all times, and there are usually a few spares up there in case one of them fails. They're up about 12,000 miles. They're in inclined orbits. I discussed the inclination of orbits back in the lecture on spaceflight. These orbits are inclined at 55 degrees. That's a fairly high inclination, and it allows them to be seen then from anywhere on Earth. The orbital shape is circular, and the orbital period is about 12 hours. So these are going around about twice as fast as the Earth is rotating underneath them. So those are the parameters of the GPS constellation. Now, the exact orbits are monitored from the ground. So we know exactly how the satellites are moving. Furthermore, because they're up at 12,000 miles, there's essentially no air resistance, and their orbits are very accurately predictable. So we monitor those orbits. We occasionally, actually more than occasionally, sometimes as often as every hour, send information to the satellites telling them exactly where they are. So the satellites know that information. And then, given that the orbits are very predictable by Newton's laws, they continue to know very accurately where they are for some time to come. And they continually broadcast signals that carry information about their precise positions. GPS satellites typically last somewhere on the order of 7 to 15 years, and then they're continually being replaced, and the newer satellites tend to have better capabilities, more accuracy, and so on. So how does GPS work? Well, fundamentally, it works by measuring the distances to, in principle, 3, in practice 4, and I'll tell you why the 3 versus 4, of the satellites, and using the measured distances to determine exactly where on Earth an observer is. So what a GPS user sees is the following. A GPS user is sitting here on Earth, and the system is set up, the constellation of satellites is configured so that a given observer always sees at least 4 satellites. There are always at least 4 satellites in the sky above you if you're using GPS, and those 4 satellites are always above the horizon. They're not always the same 4 satellites, but you'll always be in view of 4 satellites. And the question is, how far is it to each of those 4 satellites? If you can answer that question, as I'll show you, you can pin down your position with incredible accuracy. Well, let's see how that works. You probably have used at some point or learned about a technique called triangulation to measure distances. For example, I was talking to a biologist recently who was measuring the heights of the trees in a tropical rainforest. And the way that was done was to measure the distance from the base of the tree to the observer. The observer then sights up to the top of the tree, and knowing that angle and a little trigonometry, you can calculate the height of the tree. That's triangulation. GPS uses kind of the opposite. It finds out where you are by determining distances. Triangulation determines distances by knowing where you are and some other measurements. The GPS satellite measurements determine where you are from distance measurements, and that's a process called trilateration. I'm going to describe that process, and I'm going to describe it first in 2 dimensions because it's easier to understand what's going on in 2 dimensions. I've got a 2-dimensional screen, and so I'm going to describe the picture in 2 dimensions. I will then show it to you in 3 dimensions, which gets more complex. And occasionally throughout this discussion, I will drop back to 2 dimensions just to make the picture simpler. But remember, all this is going on in 3 dimensions. So how does this work? Well, here's a GPS satellite. And suppose I somehow know how far I am from that satellite. And I'll show you shortly how we, in fact, know how far we are from the satellites. Well, all that tells me is the distance. I might be at the end of that blue line. I might be at the end of that equal length blue line. I might be at the end of that equal length blue line. In fact, again, in 2 dimensions only, I might be anywhere on a circle whose radius is this known distance to that satellite. So all that distance measurement tells me, if I know I'm 12,340 miles from that satellite, all that tells me is that I'm somewhere on a circle, and in 3 dimensions it would be a sphere, whose radius is that distance, but it doesn't tell me where on that circle. But remember, there are more satellites in my field of view. So here's another satellite, and maybe I'm a little farther from that satellite. So I know I'm on a circle whose radius is the distance I know I am from that satellite. And in 2 dimensions, those 2 circles intersect in only 2 points. There they are. And so I know, in principle, that I'm at one of those 2 points. And it turns out the ambiguity between which of those 2 points I'm at can usually be solved. One of those points will typically be way up in space off the surface of the Earth, or maybe it'll be down inside the Earth, but one of them is on the surface of the Earth. And that's enough to tell me where I am in 2 dimensions. So trilateration in 2 dimensions requires, in principle, measurements of the distances to 2 different satellites, and that pins down my position to within 2 possible points, one of which can usually be rejected because it's obviously absurd. Well, the world is not 2-dimensional, it's 3-dimensional. So we need to do this process in 3 dimensions. That's a harder picture to draw, but let me give you a sense of how that works. So here we are now in 3 dimensions. Again, here's a GPS satellite. Here's a sphere surrounding that satellite, because in 3 dimensions, if I know the distance from myself to the satellite, all I know is that I'm on a sphere in 3 dimensions on the surface of a sphere whose radius is that distance that I know to that satellite. Well, here's a second satellite. Same one I was talking about before, but now instead of being on a circle about that satellite, all I know is that I'm on a sphere whose radius is equal to the known distance to that satellite, but again, I don't know where I am on that sphere. Put together the information from those 2 satellites, and you can see from this picture that the 2 spheres intersect in a circle. So now what I know is that I'm on a single circle. 3 dimensions makes things more complicated. In 2 dimensions, 2 satellites were enough to tell where I was to within this ambiguity. In 3 dimensions, all they do is put me on a circle, what 1 satellite did in 2 dimensions. But the world is 3-dimensional, so here's where we are. So we need a 3rd satellite. If there's a 3rd satellite, and I know I'm a certain distance from that satellite, then I know I'm also on a sphere that surrounds that satellite and whose radius is the known distance to it. And if you look at the picture, you see that those 3 spheres intersect in ultimately 2 points. So then with 3 satellites, I know I'm on one of those 2 points. And again, one of them is usually absurd. It's way up in space. It's down inside the Earth or something. And so we can easily pick out which one I'm on. That's great. So that is, in principle, how we determine our position on the surface of the Earth. How do we determine it within a few feet? Well, that's where we're going in the rest of this lecture. It's a little bit more subtle than just doing this, as we'll see. How do we determine the distance? Well, the distances are determined ultimately by timing radio signals coming from the satellites and using the known speed of light to calculate the distances to the satellite. The speed of light is fast, but we can nevertheless use it for timing. And if we had perfectly accurate clocks in the satellites and on the ground in the receiver we use, we could in fact measure that time with exact precision, and with the exception of some problems I'll bring up in a minute, we could determine our position. Now the satellites have on board them very, very accurate atomic clocks. They're good to about 10 billionths of a second. And I want to digress for a moment about how atomic clocks work, because they're the essence of the GPS technology in a sense. They're also the essence of how we keep time here on Earth in general. So let me just take a little digression and tell you what an atomic clock is. Atomic clock is a rather sophisticated thing. It consists typically of a generator of microwaves, some kind of cavity into which those microwaves are beamed, a non-uniform magnetic field, and I'll tell you in a minute what that does, and an atom detector. Now, our standard of time is in fact based on transitions among energy levels in atoms. I talked about such transitions back when I was talking about how semiconductors work, for example. And in particular, the atom cesium undergoes a very so-called hyperfine transition between 2 very closely spaced energy levels, and it emits in the process electromagnetic radiation at a precise frequency. And our definition of the second, what 1 second means to humankind these days, is 9,192,631,770 oscillation cycles of the energy associated with that transition in the atom cesium. That's how a second is defined. And atomic clocks reproduce that transition. Here's how it works. We send a beam of atoms through this cavity. And if the atoms get bumped up into that slightly higher energy level, which they will do if we bombard them with microwaves of just the right frequency, then when they pass through that non-uniform magnetic field, they will be deflected upward into that atom detector. If they haven't been bumped up to that slightly higher energy level by microwaves of just the right frequency, they will be deflected downward. So what we do is have a control loop, a feedback loop, that looks at the number of atoms coming into that detector and changes the frequency of the microwave generator, which is what's bumping those atoms up, in such a way as to maximize the number of atoms coming into that atom detector. And when we get the maximum number of atoms, we know we've got the microwave frequency at exactly the frequency the atoms want to undergo that transition at. Now there's some subtleties. The atoms have to be cold. Sometimes we actually drop them down in a big tower. But ultimately, we connect a digital counter to that microwave generator. We know those microwaves are at the right frequency to excite that transition in the atom, and so we're there right at that frequency, and from that we can actually tell the time. The United States Standard of Time, which you can get off your computer, you can in fact synchronize your computer's clock to the standard, or maybe you have a so-called, quote, atomic clock at home, which is not an atomic clock, but simply a clock with a receiver that gets the signal from the U.S. standard atomic clock. You're looking at signals from this clock. This is the U.S. official time standard, the NIST F1 cesium atomic clock. NIST is the National Institute of Standard and Technology. And here is their F1 cesium atomic clock. This is a bigger, more sophisticated clock than on the GPS receivers, and it's what sets the standard of time for the United States. So now we know how atomic clocks work. Back to GPS. GPS satellites carry 4 different atomic clocks. Some use cesium, some use rubidium, but they basically work on this same principle. By the way, GPS is then broadcasting a time signal, so it can also be used to set your time, and GPS receivers know what time it is because of that. Now, each satellite sends out a unique signal that identifies that satellite. It's a so-called pseudo-random code. It's a string of ones and zeros. And here's what happens when you're using GPS to try to figure out where you are. There's a particular satellite up there in space. It's over the horizon. You can see it. Your receiver knows these pseudo-random codes for all the different satellites, so your receiver identifies what satellite that is, and it produces in itself this pseudo-random code. You get the pseudo-random code from the satellite, but it comes to you a little bit delayed. And that time delay tells you how long it took the signal to get from the satellite to you. That's what determines your distance from that satellite. Remember, we had to know distances to 3 satellites. And here's a little math. The speed of light is about 186,000 miles a second. The satellites are up about 12,000 miles. So the time it takes to get from the satellite to you is about 12,000 miles divided by 186,000 miles a second. That's about 6 or 7 hundredths of a second, about 65 milliseconds. Pretty small time. If those timing were off by even a thousandth of a second at 186,000 miles a second, your distance would be off by 186 miles. And GPS is good to 10 feet, sometimes to inches. How do we achieve that? Well, we got to look into a few other things. First of all, your receiver is not a great big heavy thing with an atomic clock in it. We can't afford to put an atomic clock or afford to fit one in the receiver, so it has a more standard quartz clock like your quartz watch. We have to somehow correct the fact that that clock isn't really good enough. Here's how we do it, and this is a 2-dimensional analogy. Remember, if we had 2 satellites and distances to them, we would know exactly where we were in 2 dimensions, or we'd know to within those 2 points. What if we had a 3rd satellite also? Well, we would, presumably, its circle would also have to intersect at that point, because we are at a specific place after all. So this is the ideal. There's perfect agreement. But because the clock in your receiver is not that accurate, there's some error. There's an uncertainty in the distances because of that clock error in your receiver. So what do? Your receiver cleverly looks at that error, only it does this with 4 satellites because it took 3 satellites in 3 dimensions to pin us down, but with the clock errors that isn't good enough. We take the measurements from a 4th satellite. If they're inconsistent, which they will be because of these timing errors, we then recalculate. Your receiver recalculates all the distances in order to find the unique solution that puts those at the same place, and then your clock is corrected and matches the GPS transmitter clock in the satellite. So that's why we need 4 satellites, 3 in 2 dimensions, 4 in 3 dimensions, and the result is a measurement that's typically good to within a few tens of feet, and I'll get to that in just a moment. In addition to position, GPS receivers also measure the relative velocity. They do that by the Doppler shift, so if you're driving along the countryside, the GPS receiver can calculate how fast you're moving. There are a number of other errors that we have to correct for, or at least take into account. For instance, the satellite's positions are known, but not absolutely perfectly. They're typically good to about 10 feet. So there's a 10-foot error. The clocks in the satellites are good to about 10 billionths of a second. Light travels about a foot in a billionth of a second, so there's another 10 feet. A more subtle error is Earth's upper atmosphere. The satellites are up at 12,000 miles. We know the exact speed of light, 299,792,458 meters per second, exactly by definition. We know the speed above the atmosphere. But in the atmosphere, only about 100 miles or so, depending on what angle we're coming at, the speed is affected by atmospheric conditions. And here I want to draw on the module on electromagnetism a little bit, because here's why this happens. About 50 miles up, there's a layer of the atmosphere where high-energy radiation from the sun, ultraviolet and so on, have ionized some of the atoms, and there are a number of free electrons around there. And Earth has a magnetic field. And those electrons are doing what electrons do in a magnetic field. They're experiencing magnetic forces. They're charged particles, moving charged particles. and they go spiraling around the magnetic field lines, and that has a profound effect on radio waves coming through. Those rotating electrons interact with radio waves and slow them down. And the amount by which they slow them down depends on how many of these electrons there are, and that depends on local conditions and what the sun is doing and so on, and is quite variable. So that's a hard thing to compensate for. However, fortunately, that effect is frequency dependent, and the satellites broadcast signals at two different frequencies. So here come signals from two different frequencies. They come out of step with each other. Each one has been slowed down by a different amount, and by determining that amount, we can determine what the ionospheric conditions are, and we can sort of correct for that. Our corrections bring that error to about 15 feet. Another thing that happens is the signal from the satellite is supposed to come directly to your receiver, but what if there's a tall building nearby or a body of water or something? The signal bounces off and it comes to your receiver, and this is sort of like when you see ghost images on your TV. The little ghostly image you see maybe to the right is from a weaker signal that has come a little bit later into your TV receiver by bouncing off some object in your environment. So this multipath error is a problem, and it typically amounts to about 2 feet. And the receiver has sophisticated algorithms for trying to figure out which signal gets to it first. So there are a variety of error sources in GPS. There's the positions, about 10 feet, the satellite positions. Their clocks, another 10 feet roughly. Atmospheric error, about 15 feet. Multipath error, another 2 feet. And the result is typical GPS accuracy is a few tens of feet. You know where you are on the surface of the Earth to a few tens of feet. By the way, there's another very subtle effect or sophisticated effect that would cause errors, except we know to correct for it. Both Einstein's special theory of relativity and general theory of relativity talk about things that happen to time when an object is moving relative to you. The satellites are moving relative to you, not fast compared to c, the speed of light, but still pretty fast. And they're up high where gravity is different, and both special and general relativistic effects have to be taken into account. If they weren't, by the end of a day, the measurements made by GPS satellites would be off by about a mile. So there's one case where Einstein's theories are really everyday physics. Now, I've got us down to a few feet, but we can do much better than that. And we do that with so-called differential GPS. And here's how differential GPS works. You have a second receiver, and you put it at a fixed location and a known location, a location that's been surveyed so we know exactly where on Earth this location is. And that second receiver, which may be up to 100 miles or so from where you're doing your work, is at a known location. It's close enough to you that atmospheric conditions above you and that receiver are the same, roughly, closely. So we can compensate for that error completely. We can get rid of atmospheric error completely. Furthermore, because this satellite, this receiver knows exactly where it is, the errors in its measurement as determined by GPS, it can correct for those errors, and it relays all those corrections to you in your nearby roving GPS. And with differential GPS, you can easily get down to a few feet, and with really sophisticated techniques, you can get down to a few inches. So that's differential GPS. Well, what do we use this GPS for? I'm just going to give you a brief introduction to the many, 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 many ways GPS is used in today's world. For example, GPS is increasingly built into cell phones, so that if a cell phone call is made to 911, an emergency call, the 911 operator immediately knows where the cell phone is. That was a weak link in the whole 911 system. When we got landline phones so that the 911 operators knew where they were, that didn't work for cell phones. Well, cell phones can identify themselves possibly by triangulation to cell phone towers nearby, but with GPS, anywhere on Earth, a cell phone could figure out exactly where it is and send that information to 911. Handheld GPS is great for hikers, boaters, and so on, and here's a picture of a hiker with a handheld GPS receiver looking off in the mountains and knowing exactly where they are. We use GPS navigation in cars. Increasingly, cars are coming with built-in GPS navigation systems, or you can buy them as add-ons. They include things like road maps that show exactly where you are, and some of them will even speak directions to tell you where to turn. If you go into a canyon between buildings in a city or through a tunnel, there are auxiliary systems based on your car's odometer and acceleration measurements that continue to tell you where you are until you're back in view of the satellites again. We use GPS for tracking in a variety of applications. For example, a freight company might want to know exactly where its trucks are at all time. So its trucks are equipped with GPS receivers. The GPS receiver knows where the truck is, and then a transmitter on the truck beams that to the company's headquarters. So it knows exactly where its trucks are, when they're going to arrive at their destinations, if its drivers are goofing off by the roadside rest area for too long, or whatever. And there are a whole bunch of other applications for vehicle tracking. Emergency vehicles and taxi fleets are tracked this way. That provides the most efficient deployment of vehicles to where they're needed, for example. Rental car companies are increasingly using GPS. I recently read of a case where a person had rented a car in California, and the rental agreement said you must stay within the state of California. They decided to go to Las Vegas, which is not very far from the California border, but far enough that a GPS device in the car recorded that straying over the state line, and they were hit up with a fine or something when they got back. If you're an anxious parent, you can actually have a covert GPS recorder installed in your car. You want to know where your teenagers are going with the car, and it will record every move of that car, and it can come with maps of your area. So it will tell you, when you play it back, exactly what street they've been on, and you download this thing into your personal computer. Or if you're some kind of covert operative who wants to track somebody, these things are being done now. Farmers like GPS. Farmers waste a lot of fuel plowing over the same ground twice or overlapping their plow or whatever. Well, farmers can use GPS. They reduce fuel consumption when they do that, and they also reduce the time it takes to plow a field. And here's a picture showing symbolically a tractor pulling a plow, plowing these nice straight furrows. How does that work? Well, straight GPS tells the tractor where it is to within a matter of a few tens of feet. That's certainly not good enough to plow a nice straight row and get the next one right parallel to it and not overlapping but not leaving any gap in between, or getting it positioned where you want it to be. So you set up a differential GPS. In this case, you don't need to know exactly where the differential GPS transmitter is. All you've got to know is where you are relative to it, and that's real easy. So here's a differential GPS receiver at the edge of the field. It gets that information, and then it becomes very easy to measure the tractor's position to within inches relative to that differential GPS receiver. And so that allows the farmer really to save a lot of fuel, cutting down on those energy servants that I talked about in a previous lecture, by the way, if you want to think about some of the implications of that. Now, GPS does not only give position in terms of latitude and longitude on Earth or on a map that's built into a GPS receiver, it also tells your altitude, tells how far above the ground you are, because it finds your position in 3 dimensions. So it's ideally suited to aircraft navigation. And one system that went into effect in the in 2003, I believe, the Wide Area Augmentation System is designed to bring the benefits of instrument landing systems to small airports that didn't have them before. And here's how it works. We've got a jetliner with GPS, and so it's looking at some GPS satellites and getting approximate information on its location, but not good enough to land with. Good within a few tens of feet. You might miss the runway at that rate. Well, deployed around the United States are 25 reference stations which receive GPS signals. And they send those signals to central transmitting stations, which beam them up to a geosynchronous satellite. Remember, those are those satellites up 22,000 miles that rotate once in 24 hours and so stay fixed above a given location on Earth. And the geosync satellite beams all the information back to the aircraft and can tell the aircraft exactly where it is. And so an airport that does not have instrument landing systems, this can take the place of instrument landing systems, and smaller airports can then be open to the kind of navigation that only larger airports had before. By the way, another advantage of this is it may save fuel because it may allow flight controllers to vector aircraft on paths that take them straight from one airport to another instead of going in roundabout paths as required now by air traffic control. Well, there are a whole lot of other uses of GPS in science and engineering and business and so on. For example, if you're a scientist studying wildlife, you can stick GPS receivers on your wildlife. The GPS satellites locate the wildlife, and then a transmitter on the little collar device the elephant here is wearing tells you, the biologist, just where the elephant is, and you can track it around. Oceanographers scatter GPS off the ocean surface, and they can use that to calculate the wind speed at the surface. Engineers worrying about dams breaking or bridges deforming put GPS receivers on them, and they can actually measure the slight motions due to that deformation. Geologists monitor the growth of the flow of glaciers and even continental drift, with the growth of mountains with GPS. GPS is everywhere. You may not realize it yet, but GPS is almost certainly already a part of your life. And it's going to become more a part of your life in the future. Just some examples. GPS tracking of your children, possibly, of your pets, of your possessions. GPS will at some point give us more intelligent cars and highways that may be able to drive themselves because they'll know precisely where they are and where the cars around them are. We'll have improved GPS capabilities in the future, consisting of greater power, more frequencies, more of them civilian accessible, more sophisticated timing, more pseudo-random codes to the underlying linked to the underlying radio signals, and more power and a whole bunch of new capabilities and less interference. GPS is truly going to be a part of your future, and it's truly part of physics in your life.